The film opens in silence, a silence so vast it seems eternal. Across the infinite canvas of night, the stars thin. Galaxies drift farther apart, stretched upon the expanding fabric of spacetime. What began as a universe ablaze with fire, a storm of fusion and light, moves steadily toward darkness. One by one, the great furnaces of creation exhaust their fuel. Black holes feed upon suns, swallowing the remnants of brilliance. The cosmos, once radiant and alive, grows dim. This is the fate written into the equations of physics. Entropy, the inevitable tide. Order dissolving into chaos, energy dispersing until no flame remains. And yet, even in this encroaching night, a question lingers like a whisper. Is there a final lantern at the end of the universe? A last glow in the silence? A remnant of structure in a sea of decay? Cosmologists speak of endings with caution, of a heat death where the cosmos fades to uniform cold, of a big rip tearing even atoms apart, of a slow fade into unrelenting stillness. But hidden within those scenarios lies a haunting possibility, that something endures, some luminous trace born not of stars, but of the laws themselves. Perhaps it is the slow evaporation of black holes, releasing Hawking radiation into the void. Perhaps it is the faint decay of protons, the last whisper of matter dissolving into light. Or perhaps it is something stranger still, the survival of information, flickering as memory across the very skin of spatian, of the lantern at the end. Of the universe is not a beacon we can sail toward. It is the ultimate riddle of physics. What remains when time itself has exhausted all things? The story of the lantern at the end of the universe begins not with telescopes or equations, but with the oldest human impulse to look upward. For tens of thousands of years, the night sky has been a canvas upon which civilizations projected myth, prophecy, and fear. In Babylon, priests carved star charts into clay, seeking the rhythms of eternity in the movements of planets. In Egypt, constellations rose over pyramids aligned with precision, as though stone itself were placed to catch the memory of the heavens. The Greeks spoke of cycles, worlds born, destroyed, and reborn, while the Norse envisioned Ragnarok, a final twilight when even gods would perish in fire and ice. Everywhere, across cultures, the same haunting idea lingered, that what begins must one day end. Yet in those myths, endings were never absolute. Fire returned, cycles turned, and the universe renewed itself. Eternity was never questioned. The cosmos itself was assumed to be infinite, unchanging, the eternal stage upon which human dramas unfolded. This conviction endured into the dawn of science, and for centuries it held. In the 17th century, Isaac Newton described the universe as a vast clockwork machine. Space was absolute, stretching without boundary. Time ticked uniformly, indifferent to the rise and fall of stars. In Newton's vision, the cosmos was eternal, infinite, unbreakable. The lantern at the end of the universe did not exist, because the universe itself was its own unending flame. But Newton's cosmos was not the last word. 3 centuries later, Albert Einstein shattered the illusion of eternity. In 1915, he presented his theory of general relativity, a vision of space-time as something living, elastic, curved, capable of bending under the weight of mass and energy. The cosmos was no longer an eternal stage. It was an actor in its own drama. In the equations of relativity, Einstein glimpsed something astonishing, a universe that could not sit still. Left to itself, Spacetime must expand or contract. An eternal, unchanging cosmos was impossible. Disturbed by this conclusion, Einstein inserted a corrective term into his equations, the cosmological constant, a kind of cosmic repulsion designed to hold the universe in static equilibrium. To him, the cosmos was still eternal, balanced like a lantern that never dimmed. Yet this was only a temporary illusion. In 1929, Edwin Hubble pointed the telescope at distant galaxies and discovered the truth Einstein had tried to resist. Galaxies were receding from one another. The fabric of space-time itself was stretching. The universe was expanding. Suddenly, the eternal clockwork broke. If the universe was expanding, it must have once been smaller. It must have had a beginning. A beginning meant, inevitably, an ending by the mid-20th century. The Big Bang Theory emerged. Georges Lemaitre, a Belgian priest and physicist, suggested that all things had expanded from a primeval atom. Fred Hoyle, who resisted the idea, mockingly named it the Big Bang. Yet the name endured. In 1965, Arno Penzias and Robert Wilson detected the faint static of the cosmic microwave background, the afterglow of creation itself. The evidence was undeniable. The universe had been born in fire, and if it was born, then it would die. The second law of thermodynamics gave shape to this haunting destiny. Entropy, the measure of disorder, always increases. Stars shine because they burn their fuel, releasing energy into space. But in doing so, they drive the cosmos toward equilibrium. Every act of order comes at the cost of greater disorder. In this light, the universe is not a cycle, but a one-way descent, a march toward maximum entropy, toward heat death, a state where no energy gradients remain, no work can be done, no stars can shine. But even this was only the beginning of the shock. In 1916, Karl Schwarzschild provided the first exact solution to Einstein's equations describing an object so dense that space-time itself folded inward. Black holes were born, though no one yet believed they could exist. Through the work of Penrose, Wheeler, and Hawking, these monsters of gravity emerged as real, not just mathematical. By the late 20th century, astronomers found them at the centers of galaxies, swallowing light itself. Black holes introduced a new actor into the story of endings. If the universe was to die, what role would these cosmic engines play? Would they be the final lanterns, dark yet powerful, dominating the far future, or would even they fade? It was Stephen Hawking who answered. In 1974, he showed that black holes are not eternal. Through quantum effects near their horizons, they radiate energy, what is now called Hawking radiation. Slowly, over unimaginable timescales, they evaporate. The devourers themselves are doomed. Even these titans fade into nothing. Suddenly, the end of the universe grew darker still. If black holes could die, then nothing was eternal. Not stars, not galaxies, not even matter itself. For, if protons, the most stable particles known, can decay, some theories suggest, then matter too is temporary. Even the atoms in every living being may one day dissolve. From ancient myth to Newton's eternal cosmos, from Einstein's curved space-time to Hawking's fading black holes, the story had transformed. The universe was no longer infinite clockwork, but finite, fragile, fleeting. The lantern at the end of the universe could no longer be a star. It could not be a galaxy, nor even a black hole. It must be something else, something hidden in the very laws of physics. Perhaps a faint glow that persists after matter is gone. Perhaps the whisper of information encoded in the structure of spacetime. Or perhaps nothing at all. By the close of the 20th century, one more discovery deepened the mystery. In 1998, astronomers observing distant supernova found that the universe's expansion was not slowing down, it was accelerating. Dark energy, a force woven into the vacuum itself, was driving galaxies apart faster and faster. If it continued, the universe would not merely fade, it would tear itself apart. The cosmos, once assumed eternal, was now a story with an ending. And within that ending, physicists began to ask, what is the last light? What is the final lantern? The discovery phase ends with this haunting realization. Every structure in the universe is temporary. Stars fade, galaxies scatter, black holes evaporate, even atoms may one day dissolve. The only permanence is impermanence, and yet the question remains, what flicker, however faint, might remain when all else is gone? The revelations of the 20th century struck like thunder across the serene assumptions of eternity. Humanity, long accustomed to seeing the cosmos as unshakable, was confronted with a universe that not only had a beginning, but a trajectory toward an ending. What began in brilliance would not last. The stars were not infinite torches. They were fragile fires, consuming themselves in silence. The first tremor of shock lay in the discovery that the universe is not eternal. The expansion revealed by Hubble shattered Newton's infinite clockwork and Einstein's dream of balance. A universe with a beginning carried with it an unavoidable implication. It would also have an end. The second law of thermodynamics whispered of that end with merciless clarity. Entropy increases, heat dissipates. Every star that burns adds to the tally of cosmic disorder. The final state, known since the 19th century, would be equilibrium. No gradients, no energy flows, no life, no fire. A heat death. But this was only the surface of the shock. The deeper revelations came not from thermodynamics, but from the strange marriage of relativity and quantum mechanics. In 1974, Stephen Hawking made a discovery that unsettled even the foundations of physics. Black holes, once imagined as eternal, prisons from which nothing escaped, were shown to leak. At the event horizon, quantum fluctuations created pairs of particles. One fell inward, the other escaped, radiating into the universe. Slowly, almost imperceptibly, the black hole lost mass. Over unimaginable spans of time, it would evaporate entirely. The devourer itself would vanish. The implication was staggering. Nothing in the cosmos was immortal. Not stars, not galaxies, not even black holes. In a universe where even the darkest giants fade, permanence was revealed as an illusion. This discovery unleashed another, even darker paradox, the information problem. If black holes evaporated, what became of the information encoded in the matter they swallowed? Quantum mechanics insisted that information could never be destroyed, but Hawking's theory seemed to suggest the opposite. If true, the very foundations of reality, quantum mechanics itself, would fracture. The lantern at the end of the universe would not only be dim, it would be paradoxical, a light that both existed and did not dot, parallel to this shock. Cosmology was unraveling its own revelations. In 1998, two teams studying distant supernova uncovered the unthinkable. The expansion of the universe was not slowing, as gravity should dictate, it was accelerating. Some unseen energy, a pressure built into the vacuum itself, was pushing space-time apart faster and faster. This dark energy, now known to constitute nearly 70% of the cosmos, transformed humanity's vision of the end. No longer would the universe gently coast into heat death. Instead, galaxies would be carried beyond one another's horizons. In the far future, every island of stars would vanish from view, leaving observers any remain trapped in isolated pockets of silence. The universe was not just dying. It was erasing its own history, hiding its own past. For scientists, this discovery was not merely unsettling, it was devastating to the imagination. The lantern at the end of the universe could not be found in stars, for they fade. It could not be found in galaxies, for they scatter. It could not be found in black holes, for they evaporate. And it could not be found in the universe itself, for its very fabric accelerates into dissolution. Even matter, once believed indestructible, faced its own mortality. Protons, the stable building blocks of atoms, might not be eternal. Theories of grand unification suggested that after 10 cubed J years or more, protons could decay, dissolving into lighter particles. If true, then everything stone, planet, star, and living being was a temporary arrangement. The lantern of existence burned not with permanence, but with borrowed time. The shock here was not only scientific but philosophical. For centuries, permanence was a comfort. The stars seemed eternal. The earth seemed solid. But now, at the most fundamental level, impermanence reigned. What humanity called forever was only a pause in the slow unraveling of being. Worse still was the scale of the revelations. Physics predicted the heat death of the universe at timescales so vast they defied comprehension to the power of 100 years. A number with more zeros than atoms in the cosmos. Black holes, too, lived and died across unimaginable spans. The lantern at the end of the universe was not an object one might see, but a concept whispered across infinite epochs, and yet, in this immensity, the lantern itself grew stranger. If black holes evaporated, they left behind not only radiation, but perhaps a final burst, a release of the information they had long imprisoned. If protons decayed, they would emit faint light and energy as they dissolved. If dark energy endured, the vacuum itself would glow with a relentless, invisible push. The lantern was no longer a star. It was the laws of physics themselves unfolding. In their last quiet acts, the deepest shock came from confronting the possibility that even nothingness was unstable. Quantum field theory suggested that the vacuum itself might not be the lowest state of energy. If the universe rested in a false vacuum, it could collapse into a deeper state at any moment. Such a collapse would expand outward at the speed of light, erasing everything galaxies, atoms, even spacetime itself. The lantern at the end of the universe might not be a slow fade at all, but a sudden extinguishing, a flame snuffed out before it reached its natural end. For Einstein, the cosmological constant was once a mistake, a patch to preserve eternity. For Hawking, the evaporation of black holes revealed the fragility of permanence. For cosmology, the discovery of dark energy transformed the end into a horizon of silence. Together, these shocks built a new understanding. The universe was fragile, temporary, and haunted by impermanence. The lantern, then, was no longer a metaphor for light, but for survival. What remains when nothing remains? What persists when even the stars fade? For the first time in human history, the question was no longer myth, it was physics. The lantern at the end of the universe was not a poetic speculation. but a problem inscribed in equations, tested in data, glimpsed in the faint radiation of distant stars. And the shock of it all was not only that the universe would end, but that its ending was already written into its beginning. Entropy, dark energy, evaporation, decays were not accidents of time. They were the deep structure of existence. The lantern was not an escape. It was the truth. By the close of the 20th century, humanity stood face to face with a cosmos that was not infinite, not eternal, and not secure. The lantern at the end of the universe remained a mystery, but the shock was clear. Nothing lasts. Not even nothing. To search for the lantern at the end of the universe is to search for echotraces of what has already happened, projections of what must come, and models that bridge the gap between the two. If the opening shock revealed the impact of stars, galaxies, and even matter itself, the deeper investigation sought to chart the pathways of that impermanence, to map the slow descent of the cosmos into its twilight. The first step in this investigation was the building of time. Cosmologists began to imagine the future of the universe not in centuries or millennia, but in intervals so vast they stretch beyond ordinary comprehension. At roughly 10 trillion years into the future, the last generation of red dwarf stars is expected to burn out. These are the smallest and longest living of suns, glowing faintly compared to stars like our sun, but capable of enduring for trillions of years. When their fuel is spent, no new stars will form. The cosmos will enter an era known as the degenerate age. Here, stellar remnants dominate: white dwarfs, neutron stars, and black holes. These embers of creation persist in silence, slowly cooling, their light fading toward invisibility. White dwarfs will crystallize into spheres of carbon and oxygen, essentially giant diamonds adrift in the night. Neutron stars, dense as mountains compressed into sugar cubes, will remain, though their pulses weaken. The universe will no longer blaze, but only whisper. Beyond these timescales, the narrative stretches further still. At around 10 years, black holes take the stage. No longer just the graveyards of stars, they become the universe's final engines. Their immense gravity continues to consume matter, swallowing the last drifting debris of galaxies. But thanks to Hawking's insight, their fate is now understood differently. Instead of lasting forever, they leak. Slowly, relentlessly, black. Holes evaporate through Hawking radiation. For small ones, this process is swift by cosmic standards. For the titanic, supermassive black holes at galactic centers, evaporation may take 10 years or more. When they reach their final moments, their death throes release bursts of energy, like fireworks at the end of time. These fleeting flashes could be among the last true lanterns in a fading universe. The investigation of this long cosmic future rests not only on theory but on data. Observatories have mapped the early universe in exquisite detail, allowing scientists to simulate its later stages. COBE, WMAP, and a Planck satellite traced the faint afterglow of the Big Bang to the cosmic microwave background with increasing precision. These maps reveal tiny fluctuations, quantum ripples stretched across billions of years, that seeded galaxies themselves. The same tools, extended forward in time, let cosmologists predict how galaxies will scatter and vanish across horizons, and how entropy will creep toward its maximum. Each of these missions confirmed something startling. The laws that shaped the universe at its birth are also writing its ending. Inflation seeded the galaxies. Gravity sculpted them. Dark energy now scatters them apart. Entropy measures their decay. The lantern is not a new phenomenon, but the continuation of an ancient script. Another layer of investigation probed the stability of matter itself. If protons decay, the fabric of atoms will dissolve. Experiments like Super Kamio Konde in Japan submerged vast detectors deep underground, searching for the faint signs of proton decay. None have been found so far, but the limits continue to tighten. If the decay exists, it occurs only after trillions of times the universe's current age. And yet, the possibility alone suggests that matter itself is not eternal. The lantern, in this scenario, becomes the faint light of decay, the final radiation of protons as they dissolve into lighter particles. Not a flame, but a whisper, sustained. Across unimaginable time, the investigation also turned to black holes, those enigmatic lanterns. LIGO and Virgo, gravitational wave observatories, opened a new window by detecting collisions of black holes. These ripples in spacetime confirmed predictions of general relativity and allowed glimpses into the life cycles of the most extreme objects. If black holes truly evaporate, as Hawking proposed, the gravitational wave observatories of the future may one day detect their last sighs, the trembling of spacetime as the universe itself exhales. But even in the deep night, the vacuum is never entirely silent. Quantum field theory insists that fluctuations remain, popping particles in and out of existence. This vacuum energy could itself be the lantern, the faint, irreducible glow of nothingness. Indeed, dark energy, discovered through the study of supernova, may be nothing more than the vacuum's push on spacetime. If so, the lantern is not at the end but beneath everything, present even now, shaping the cosmos quietly until its final breath. The investigation grew stranger when cosmologists considered scenarios beyond heat death. What if dark energy is not constant? If it grows stronger over time, the universe could end in a big rip, tearing galaxies, stars, planets, even atoms apart. In such a vision, the lantern is not faint, but catastrophic, the violent flash of spacetime itself unraveling. Other scenarios offered hope of renewal. Some theories of quantum gravity suggest that black hole evaporation might seed new universes. Roger Penrose's conformal cyclic cosmology proposed that the death of one cosmos becomes the birth of another, with information encoded in subtle patterns in the cosmic microwave background. In this view, the lantern is not a single light, fading, but a chain of torches passed across infinite eons. Yet every model, however imaginative, circles back to the same principle. The universe has limits. Stars exhaust fuel, matter decays, horizons widen, black holes evaporate, even space-time may dissolve. The lantern at the end of the universe cannot be eternal. It is by definition the last flicker before silence. The question is not whether it exists, but what form it takes. Is it Hawking radiation, faint and cold? Is it the glow of proton decay? Is it the ceaseless whisper of quantum fluctuations? Or is it the birth of new universes, lanterns lit beyond our horizon? Supercomputers extend this investigation into realms no human can truly imagine. By modeling particles, black holes, and expansion, they project billions of years forward in mere calculations. These simulations show the slow scattering of galaxies, the quiet domination of black holes, and their eventual dissolution into faint streams of radiation. What emerges is not a narrative of destruction, but of transformation. The universe does not end in a single catastrophic blow, but in a long unraveling. Each stage a lantern passing into the next dot. And yet, hidden in these models is the strangest truth of all: the lantern may never be seen. By the time the last fires burn, no observers will remain to witness them. No galaxies, no stars, no minds. The light may exist, but in silence. The end of the universe is not only the extinction of matter, but the extinction of perspective. The deeper investigation, then, reveals two things. First, that the universe has many lanterns, scattered across its vast future. The final stars, the last black holes, the decay of protons, the whisper of vacuum energy. Second, that these lanterns exist not for witnesses, but for themselves. Their light is real, even if unseen. To ask about the lantern at the end of the universe is to ask about meaning in a cosmos that outlives meaning. The investigation answers with data, equations, and timelines, but also leaves silence in its wake. For if the lantern shines without eyes to see it, is it still a lantern? Or is the last light of the universe not physical at all, but conceptual, the act of asking the question in the first place? The deeper the investigation stretched into the far future of the cosmos, the stranger and more unsettling the picture became. The universe was no longer a simple stage fading into darkness, but a labyrinth of possibilities, each scenario more extreme, more haunting, more incomprehensible than the last. What had begun as a slow fading of stars escalated into a confrontation with paradoxes, contradictions, and unknown forces that threatened to undo the very foundation of physics. At first, cosmologists thought the end would be simple: heat death, the gradual increase of entropy until the cosmos became uniform, still, and silent. Yet the discovery of dark energy shattered this simplicity. Observations of distant supernova in 1998 revealed that the universe was not slowing down in its expansion, as once expected, but accelerating. Galaxies were not only moving apart, they were racing away faster and faster, propelled by a mysterious pressure woven into the fabric of spacetime itself. The question shifted. If dark energy is constant, the universe faces heat death. But if it changes, if it grows stronger, then the cosmos may not simply fade, it may tear itself apart. This is the nightmare scenario of the Big Rip. In it, dark energy intensifies until it overwhelms every other force. Galaxies would first drift beyond each other's reach. Then solar systems would dissolve as gravity failed to hold them together. In the final moments, atoms themselves would be shredded, the bonds of protons and neutrons torn apart by the swelling acceleration of spacetime. The lantern at the end would not be a gentle candle flickering in the void, but a catastrophic blaze, the universe itself unraveling in fire. And yet, another possibility lingers: the opposite fate. If dark energy were to change sign, if it became attractive rather than repulsive, the expansion of the cosmos could reverse. Galaxies would begin to fall back toward one another, stars and matter collapsing into an ultimate implosion, the Big Crunch. In this scenario, the lantern is not fading starlight, but the conflagration of all matter, the universe collapsing into a final firestorm of unimaginable density and heat. Out of that collapse, perhaps, a new Big Bang could be born. Between these extremes lies the most chilling possibility of all: false vacuum decay. The Higgs boson, discovered in 2012, brought not only triumph but unease. Its measured mass, combined with that of the top quark, suggests that our universe may not sit in a perfectly stable state, but in a false vacuum, a precarious plateau of energy. If this plateau were to collapse into a deeper valley, a bubble of true vacuum would form, expanding at the speed of light. Within that bubble, the laws of physics themselves would be rewritten. Particles, forces, even the dimensions of reality could vanish, replaced by alien rules. The lantern here is not a flame, but avoid the sudden annihilation of everything. Without warning, without survivors, without even memory, nothing colliding with itself, nothingness unmaking everything. But escalation comes not only from catastrophe, it comes also from paradox. Black holes, once thought eternal, now pose profound contradictions. Hawking's prediction that they evaporate leads to the information paradox. If a black hole vanishes entirely, what happens to the information of everything it swallowed? Quantum mechanics insists that information cannot be destroyed. General relativity seems to suggest otherwise. Between these two pillars of modern physics lies a clash unresolved. If information is preserved, then perhaps the lantern at the end is not light but memory encoded, somehow in the very fabric of spacetime, stored on horizons or radiated outward in some unknown form. This is the essence of the holographic principle. The radical idea that everything within a region of space is encoded on its boundary, as if reality itself were projected like a three-dimensional hologram. If this principle holds, then the lantern at the end of the universe may not be photons or particles at all, but information, the eternal residue of all that ever existed, woven into the edges of space-time. Here the mystery deepens further. If space-time itself is emergent arising from quantum entanglement rather than existing as a fundamental entity, then the lantern might be something even stranger, not light, not heat, not matter, but the persistence of entanglement patterns across the cosmic void. In this vision, the ultimate lantern is the structure of reality itself, whispering across eternity that existence was never truly extinguished, only transformed. Other speculations carry the escalation into realms almost mythic. Eternal inflation, a consequence of quantum fields at the dawn of time, suggests that our universe may be only one bubble in an endless multiverse. If so, then lanterns may ignite endlessly across infinite expanses. Each universe would fade, but new ones would be born, each with different laws, different constants, different possibilities. Our lantern at the end may not be singular, but part of an infinite constellation of endings and beginnings, none final, none absolute. The escalation of this mystery is not only cosmic but existential. If entropy guarantees the fading of order, then meaning itself is temporary. If dark energy grows stronger, then the cosmos may not even fade it, may be ripped apart violently, its story cut short. If vacuum decay lurks, then existence may be less stable than a dream. And if the holographic principle is true, then perhaps nothing is lost, and the lantern is not external but internal, a light of information that persists even after all matter and time dissolves. Science does not yet know which of these fates awaits. Each is consistent with some part of the data. Each reveals a universe more fragile, more precarious, more uncanny than the last. What unites them is the realization that the lantern at the end is not ordinary. It is not a star, nor even a galaxy. It is the deepest question of physics. What persists when everything else is gone? The escalation of mystery has thus transformed a lantern into something profound. Once imagined as the last glow of dying stars, it now stretches across possibilities that redefine existence itself. It could be Hawking radiation, the faint fire of evaporating black holes. It could be the whisper of proton decay, the dissolution of matter. it could be dark energy itself, accelerating expansion into oblivion. It could be false vacuum collapse, erasing the cosmos in an instant. Or it could be information encoded forever in the holographic memory of spectrament. At the end of this escalation, one truth becomes clear. The lantern is not only a scientific puzzle but a philosophical abyss. To study it is to confront impermanence, instability, and paradox. To imagine it is to realize that the end of the universe may be stranger than its beginning. In the escalating uncertainty of cosmic destiny, science turns from evidence to possibility. When data runs thin, theory steps forwards, sometimes cautious, sometimes audacious, proposing visions of how the universe might end, and what final lantern may endure at the ultimate horizon of time. These speculations are not idle fantasies. They are grounded in mathematics, in extrapolations of known physics, and in the fragile clues left imprinted on starlight and cosmic radiation. Yet they are also deeply philosophical, for in imagining the end, one imagines the nature of reality itself. The first and most widely accepted scenario is heat death. Rooted in the second law of thermodynamics, it describes a universe condemned to equilibrium. In this vision, galaxies drift apart until no new stars can form. Black holes, once the titans of the cosmos, shrink and evaporate. Matter itself may decay, leaving behind a thin mist of photons and leptons, evenly distributed across a space too vast to comprehend. The lantern here is faint beyond imagining, the last whisper of energy, diluted to near nothingness, stretched thin across eternity. It is a lantern not of brilliance, but of inevitability, a final emberscape, where even memory is erased. But if dark energy is not constant, another fate emerges, the Big Rip. This is the most violent vision of all. If the force driving cosmic acceleration strengthens over time, its pull will overwhelm every other interaction. First galaxies, then solar systems, then planets, then atoms themselves will be torn apart. In the final seconds before the rip, molecules disintegrate, protons dissolve, and spacetime itself is stretched into oblivion. The lantern in this scenario is not a flicker, but a catastrophic blaze, the flash of existence unraveling in fire. Some physicists, though cautious, admit that this apocalyptic possibility cannot yet be ruled out. Another family of theories looks not to dissolution, but to cycles. Cyclic cosmologies, most famously proposed by Roger Penrose in his conformal cyclic cosmology, suggest that the end of one universe may seed the birth of another. In this framework, heat death is not a terminus, but a transformation. When the universe has expanded so far that matter and black holes are gone, what remains is a sea of radiation. In such a state, time and scale lose their meaning. The universe, stripped of its rulers, becomes conformally equivalent to the beginning of a new Big Bang. The lantern at the end, in this model, is not a final light, but a Bridgean echoing flare that marks both ending and beginning, a cosmic handoff from one eon to the next. Others look deeper still, toward the possibility that the lantern is not material, but informational. This is the essence of the holographic principle, drawn from the work of Gerard T. Hooft and Leonard Susskind, and reinforced by the mathematics of string theories, ADS, CFT correspondence. It suggests that everything within the universe is encoded on its boundary, like a three-dimensional world projected from a two-dimensional surface. If this is true, then nothing is ever truly lost. Even if stars die, galaxies scatter, and black holes evaporate, the information of their existence remains, inscribed in the holographic memory of spacetime. In this view, the final lantern is not a flame, but a record, the eternal persistence of all that ever was, written into the universe's last horizon. But there is a darker possibility. The discovery of the Higgs boson opened the door to the theory of false vacuum decay. If the Higgs field is not stable, then our universe may exist in a metastable state, balanced precariously atop a plateau of energy. A quantum fluctuation, at any moment, could cause it to collapse into a lower energy stator. True vacuum, a bubble of new physics would form, expanding at the speed of light, annihilating the laws of this universe and replacing them with others. In this catastrophic scenario, the lantern is no gentle flame, but the spark of destruction itself, the birth of a new cosmos inside the death of our own. It would be invisible until it arrived, sudden and final. Some scientists speculate that such transitions may have already happened elsewhere, spawning other universes beyond our cosmic horizon. Eternal inflation takes this speculation further. In the inflationary model, the early universe expanded exponentially due to vacuum energy. In some variations, this inflation never ends completely, it continues in distant regions, creating bubble universes endlessly. Each bubble has its own laws of physics, its own constants, its own potential lantern. In this multiverse, endings are local, not absolute. Our universe may fade into silence, but others will ignite anew. The lantern here is not singular, but plural, an endless scattering of lights across a sea without end. String theory and loop quantum gravity offer their own interpretations. In string theory, the universe exists within a vast landscape of possible vacuum states, perhaps as many as 500. The lantern may be the transition from one vacuum state to another, a shift in the fundamental fabric of reality. Loop. Quantum gravity, by contrast, suggests that space-time itself is discrete, woven from tiny quanta. If this is true, then the lantern may be embedded in the grain of reality itself, preventing singularities and ensuring that collapse gives birth to expansion. Endlessly. Even more speculative are proposals like Penrose's cyclic holographic echoes, in which traces of past universes are encoded in the cosmic microwave background, or the idea that quantum fluctuations in the far future could spark new universes from the vacuum of heat death. In these visions, the lantern is not only an end, but also a seed, the birth of new cosmoses from the silence of the old. At the edge of speculation lies philosophy. What if the lantern is not external at all, but internal? What if the last light of the universe is awareness itself, the human act of questioning, the cosmic curiosity that dares to imagine endings beyond sight? In this sense, the lantern is not astrophysical, but existential. It is the recognition that impermanence is not emptiness, but meaning, that fragility itself illuminates existence. Thus, the theories span a spectrum from the faint embers of heat, death, to the violent blaze of the Big Rip, from the cyclical rebirth of eons to the eternal preservation of holographic memory, from catastrophic vacuum decay to endless multiverse creation. Each is rooted in physics, yet each is also a story, a vision of what may lie at the final horizon. What unites them is the lantern itself, not as a single flame, but as a symbol of persistence. Whether that persistence is in radiation, in cycles, in information, or in new universes, it tells us that even endings are beginnings of another kind. The lantern at the end of the universe is not just a scientific prediction. It is a mirror of human longing, the refusal to let darkness be absolute. If the end of the universe is written in physics, then the task of science is to search for its handwriting, not in myth, nor in philosophy alone, but in the quiet language of data, photons gathered on mirrors, particles colliding in accelerators, ripples caught in spacetime itself. Humanity cannot wait for the deep future to unfold, must build instruments that peer ahead, reconstructing what is to come from the fragments of what is already here. Each telescope, each detector, each collider is a lantern in its own right, not of the universe's end, but of our attempt to glimpse it. The story begins with cosmic surveys, designed to map the expansion of the universe. Since Edwin Hubble first revealed the cosmic expansion, astronomers have sought to measure its rate with ever-increasing precision. Today, missions such as Euclid, launched by the European Space Agency, and NASA's forthcoming Nancy Grace Roman Space Telescope carry this quest forward. Their purpose is to probe the nature of dark energy, the mysterious force accelerating cosmic expansion, by measuring the distribution of galaxies, the bending of light through weak gravitational lensing, and the structure of the large-scale cosmos. These observatories attempt to answer a single question: is dark energy constant, or does it evolve? The answer may decide whether the universe fades gently into heat death, or is torn apart in a big rip. Closer to Earth, immense terrestrial projects also play their role. The dark energy spectroscopic instrument DESI, mounted on a telescope in Arizona, is mapping tens of millions of galaxies to chart the cosmic web with unprecedented detail. Each spectrum, each redshift measurement, is not just a snapshot of the past, it is a clue to the future, a projection of how space-time itself may unfold. In the combined light of these surveys, physicists hope to narrow the possibilities of cosmic destiny. But the universe's end is not written only in its expansion. It is also buried in the relic radiation of its beginning. For this, scientists turn to the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Satellites such as COBE, WMAP, and Planck have already mapped this ancient light with exquisite precision, revealing subtle fluctuations that seeded galaxies. Yet more sensitive missions are planned. CMBs, 4, a ground-based network of telescopes, and Light Bayard, a Japanese-led satellite mission, will push the frontier further. They aim to detect the polarization patterns that might betray the fingerprints of primordial gravitational waves. If found, these signals would illuminate the physics of cosmic inflation and the nature of vacuum energy, the very forces that may also shape the universe's end. In this way, the first light may reveal the last. Equally vital are the machines that listen rather than see. Gravitational wave observatories have opened a new era in astronomy. With LIGO and Virgo, humanity has heard the mergers of black holes and neutron stars, vibrations that have crossed billions of years. Yet future instruments, such as LISA, space-based interferometer with laser arms millions of kilometers long, will tune to lower frequencies. They will hear the whispers of supermassive black hole collisions and perhaps even the echoes of phase transitions in the early universe. Such transitions are the fingerprints of vacuum states shifting, of nothing colliding with itself. If similar transitions occur in the future, they could decide the universe's fate. Gravitational wave astronomy thus becomes a means not only of listening to the past, but of anticipating the physics that governs the end. On another front, particle accelerators probe the stability of the vacuum itself. The Large Hadron Collider, LHC, at CERN, by measuring the mass of the Higgs boson and the top quark, has already raised unsettling questions about whether our universe sits in a metastable vacuum. The precise balance between these masses determines whether spacetime is perched safely in a stable valley of energy or precariously on a plateau that could collapse into a lower state. Future colliders, such as the Future Circular Collider FCC in Europe or the International Linear Collider ILC in Japan, aim to refine these measurements with unparalleled accuracy. Their results may reveal whether the universe is fundamentally stable or destined, someday, to end in sudden vacuum decay. Beyond colliders, the quest extends to the faintest particles in existence, neutrinos. These nearly massless ghosts permeate the cosmos, relics from the first seconds after the Big Bang. Experiments like IceCube in Antarctica and the forthcoming Hypercameo in Japan seek to measure their properties with exquisite detail. Neutrinos may hold the key to understanding matter's stability, baryogenesis, and the deep structure of quantum fields. If matter itself is temporary of protons, eventually decaying trinophysics may reveal the lantern of matter's slow dissolution, glowing faintly across unimaginable timescales. And then there are the quantum-expelled small, controlled attempts to glimpse the restless energy of the vacuum. Refined tests of the Casimir effect, in which vacuum fluctuations push metal plates together, demonstrate that empty space is not empty at all. Experiments in cold atom systems create analogues of event horizons, mimicking the physics of Hawking radiation in the laboratory. Each of these table-sized experiments connects to cosmic scales, suggesting how the vacuum might flicker at the end of time, when all else has faded, to interpret such torrents of data. Scientists turn to another class of tools, supercomputers. Facilities like Summit, Aurora, and Frontier simulate the birth, evolution, and death of universes. They model black hole evaporation, proton decay, galaxy formation, and cosmic expansion across trillions of years. Within their calculations, the different possible endings are played out. Universes ripped apart, universes frozen into silence, universes reborn. These simulations are not predictions, they are rehearsals, experiments in time itself. They prepare humanity for the recognition that the cosmos is not permanent, but dynamic. Together, these tools, telescopes, satellites, interferometers, colliders, neutrino detectors, quantum simulators, and supercomputers, form a collective observatory. They are not aimed at a single star or galaxy, but at the question of existence itself. Each instrument, in its own way, peers forward through the curtain of time, asking, what is the lantern at the end of the universe? Yet the truth remains elusive. Euclid may constrain dark energy, but not define it. Like Bayard may detect inflation's signal, or it may not. The LHC may point toward vacuum metastability, but leave the timeline unknowable. Science advances in increments, in probabilities, in the sharpening of boundaries. What is certain is that these tools are humanity's only means of touching the deep future, of reaching toward an ending no witness will ever see. And in this pursuit lies a paradox. For all the instruments humanity builds, for all the data gathered, the end of the universe may never be knowable with final certainty. Some scenarios depend on constants we cannot yet measure. Others hinge on the behavior of dark energy across timescales trillions of years beyond observation. The lantern at the end of the universe may forever remain just out of reach, a light glimpsed only in theory, never in fact. Still, the attempt matters. For in building these machines, humanity extends its own lantern into the night. Every telescope that peers at distant galaxies, every collider that smashes particles together, every detector buried deep in ice or stone each, is a gesture of defiance against the silence of eternity. Science may not witness the final light, but it ensures that the question is asked, and that the asking itself becomes a kind of illumination. In the end, all the equations, all the telescopes, all the particle collisions point toward a silence not of absence, but of completion. The cosmos, once ablaze with stars, will one day lie still, its galaxies scattered like islands lost beyond one another's horizons, its stars extinguished, its black holes evaporated, its matter dissolved into faint particles drifting through endless night. This is the vision physics offers: the slow fading of everything into entropy, the dispersal of order into disorder, the extinguishing of light. And yet, within this vision, a haunting question persists. What is the lantern at the end of the universe? It may not be a star, for the stars will have long since died. It may not be a galaxy, for galaxies themselves will have scattered into invisibility. The lantern, if it exists, must be something deeper, the faintest trace of physics itself, enduring, when all structures have gone. Perhaps it is Hawking radiation, the last flicker from evaporating black holes. These titanic objects, once thought eternal, slowly bleed their energy into space, vanishing in quiet fireworks over unimaginable spans of time. In the far future, when galaxies are forgotten, their faint whisper may be the final glow, not a beacon to guide travelers, for there will be none but a testament that even darkness creates light. Or perhaps it is proton decay, the hypothetical unraveling of matter itself. If the proton is not eternal, then everything built from it will, in time, dissolve. Rocks, stars, bones, memories, all would vanish into a sea of radiation. In that vision, the lantern is not fire, but dissolution itself, the whisper of particles releasing their last energy into space, until even decay is complete, and yet other possibilities remain. Some physicists speak of information as the true lantern, for if information cannot be destroyed, as quantum theory insists, then every particle, every star, every thought leaves a trace encoded, not in matter, but in the deep structure of spacetime. In this picture, the final lantern is not light at all, but memory, the eternal record of what once was, written into the holographic boundaries of the cosmos. Even in death, the universe remembers. But what if the lantern is stranger still? What if the true survivor is not this universe, but another born from its ashes? In some cosmologies, the end is not a final silence, but a rebirth. A dying universe may seed another through quantum fluctuations, through black hole singularities, through eternal inflation endlessly bubbling into new realities. If this is true, then the lantern is transition itself, the spark of creation, igniting again and again, universes following universes in an infinite sea. For the human mind, these visions evoke both terror and awe. Terror, because they strip away permanence. Awe, because they reveal impermanence as the deepest truth. Stars, galaxies, even space-time itself are temporary, fleeting structures upon an ocean of change. To live in such a cosmos is to accept that existence is not eternal stability, but eternal becoming. And here lies the most profound reflection. The lantern at the end of the universe may not be external at all. It may not be Hawking radiation, nor proton decay, nor holographic memory. It may be the act of asking the question. For in the face of impermanence, the human mind creates its own light, the light of curiosity, of imagination, of wonder. That light burns briefly in cosmic terms, yet it transforms the cold silence of space into meaning. Consider this. Humanity exists at a privileged moment in cosmic history. The stars still shine. The galaxies are still visible. The cosmic microwave background still glows, whispering of the beginning. In trillions of years, future observers, any exist, will not see these things. The universe will have hidden its origins, erased its memory. But today, humanity witnesses both the past and the present. Today, it builds machines that stretch vision across billions of years, turning photons into stories, turning silence into knowledge. This moment is itself a lantern, burning brightly in the middle of time, and so, perhaps the lantern at the end of the universe is not a single phenomenon, but a reflection of perspective. For physics teaches that nothing lasts, not stars, not galaxies, not even spacetime itself. Yet within that impermanence lies significance. Just as a human life finds meaning not in its eternity, but in its brevity, so too does the cosmos. Its transience is its beauty. Its fading is its story. In the ancient myths, endings were not silent. They were filled with fire, with flood, with judgment, with rebirth. The universe, science now tells us, may end in silence instead. But that silence is not nothing. It is the culmination of everything, the gathering of entropy, the spreading of energy, the completion of possibility. To call it death is misleading. It is fulfillment. It is the universe becoming what it must. And yet, even as this vision unfolds, the lantern endures, not as a guiding flame for travelers, not as a beacon for civilizations, but as a symbol of continuity. Light, matter, information each plays its role in extending the cosmos beyond its apparent boundaries, and above all, the human act of seeking, of imagining, ensures that even the end is not dark, but illuminated by understanding. So when the question is asked, what is the lantern at the end of the universe? The answer may be many things. It may be Hawking's fading radiation. It may be the disintegration of protons. It may be the eternal memory of information inscribed upon spacetime. Or it may be the birth of another cosmos beyond the horizon. Of this one, but most of all, it is the lantern of thought itself, the refusal to let silence remain unexamined, the insistence on turning even the end into meaning. And so the final vision unfolds. The camera drifts outward into the cosmic night. Stars flicker, galaxies scatter, black holes dissolve. The universe itself dims, until only silence remains. But in that silence, there is still a light knot, a physical flame, not a star, but an idea. The lantern at the end of the universe is curiosity itself, burning against the void. A light that no entropy can extinguish, because it lives not in matter, but in mind.